All right, so in this video, we're going to talk about the fundamental theorem of calculus. There's going to be two parts to this. One of them we'll spend a little bit more time talking about. The second part is something we discussed in the past, and we've shown it to be true, so we can hopefully move past that one pretty quickly. But let's start here with the beginning. Let f be continuous on a closed interval ab. Part 1 states that if capital F of x is equal to the definite integral from a to x of f of t dt, then the derivative f prime of this guy, right, the derivative of that is equal to this right here, which is also equal to lowercase f of x. Now again, we're going to discuss this in great detail, but what this is essentially saying is that f is the antiderivative, which that's the whole point. It's saying that the derivative and the antiderivative are opposites of one another and they undo each other. So again, we'll come back and look at a couple examples dealing with that. Part 2, though, just to kind of summarize, if f is the antiderivative, which part 1 says it is, then the definite integral from a to b is going to be evaluated as cap f of b minus cap f of a. And we've done that in the last section. We did it several times, in fact, and we confirmed it with not only the Riemann sum problem, then we did it with the definite integral, then we did it with some basic geometry. So we see that this actually is true and does hold quite nicely. Okay, so I went ahead and cleared that second part. Again, feeling very confident that everybody understands how to use that. But this first part here is a little bit of a mess, and so I want to go through a couple examples here nice and slow. What I have up here on the screen is our f of t being t squared, and then we're on the definite interval 2 to x. And so you can see I've set up this information, this first line right here. Our capital F of x is equal to the definite integral, in our case 2 to x, and then our f of t dt. Okay? And so there's going to be a couple different things to consider as we walk through this. Now, the first thing is, if I move down, straight down, we know that if we integrate this thing as usual, we would get a 1/3 t cubed evaluated from 2 to x. And again, moving straight down, that would give us a 1/3 x cubed minus 8/3, right? If I evaluate from the top by plugging that in, minus evaluating from the bottom, that'll give us our 8/3. And so now, when we take this derivative, f prime of x, notice what happens right here. That gives us our x squared. And if you'll notice, up here in the theorem, it says that the f prime of x, the capital F prime of x, which is this guy right here, should, even though all this is in the middle and we've done all this, should always equal f of x. Well, f of x would just be this function here evaluated at x, which in this case would be our x squared. So there's our f of x. So again, we're showing that the derivative and the antiderivative essentially are opposites of one another. Okay, so now you can see I've added another part or another question to the same screen. I think it's important, especially with how messy this looks, to have not only it available, but a couple of the other things available to kind of compare. Now the big difference here, and what we're going to be doing here, is we're going to use the fundamental theorem to find dy dx. What we're going to be needing to watch out for is a chain rule in this particular case. Now when you look back up at the fundamental theorem, part 1, that x has been consistent in this last problem, right? That's because the derivative of that x is 1. Anytime you have something up here whose derivative is anything other than 1, it's going to be that chain rule. And so that's what we're going to have to worry about in this particular problem. So what we're going to do is a substitution. I'm going to let u equal x squared. If u equals x squared, now I'm going to be looking at an integral from 1 to u cosine of t dt. Okay? Now, we also know that by the chain rule that dy dx is going to be equal to dy du times du dx. Okay? So now, that's what we're searching for. We're searching for the dy dx. We're searching for the dy dx. So I'm going to come back up over here. I know that my dy dx is going to be equal to a d du now, not an x anymore, a d du. So my dy dx is going to be equal to a d du integral from 1 to u cosine of t dt. That part that I have written right there, this whole piece right here, that's my dy du, okay? Now, I still need to multiply by du dx. So I'll put my du dx off to the side, okay? Now, from this last problem here, we went through a big process to come up with what we knew was going to happen. What we knew was going to happen is when we were given something like this, the answer is always going to be just this thing evaluated at that variable. So for us, this whole thing right here is just going to be that function evaluated at that variable. So that's going to give us our cosine of u. And then when we multiply by du dx, derivative of u with respect to x is going to be a 2x. And when I put all this back together now, a dy dx is going to be 2x times cosine of u, but our u was x squared. So there's our dy dx found by using this fundamental theorem of calculus part 1. And it was a little bit of a process because this guy right here didn't have a derivative of 1, so we essentially needed that chain rule. If we write out our chain rule like we learned earlier in the course, then it falls apart quite nicely once you get familiar with this notation up here.